Thank you very much. It's good to be here. I'm excited to share some really interesting things that I've come across in the last year. So let's start off talking a little bit about quickly who I am and why you might want to listen to what I was telling people. So I started off my programming career in the early 90s working on Xenix systems, writing C code. These days, I am a contributor to a number of open source projects, including Quarkus, Vertex, Camel. I work a lot in Kubernetes and Cloud Native. I almost exclusively use Linux, and I have been doing this for quite a while, but I want to stress that I don't tend to get hung up on old patterns. I really do like to seek out and find new ways of working that are better based on new technologies. So I take my 30 years of experience and apply it with the perspective of all these new technologies that we have available to us to try and help people like yourselves learn to apply these new techniques in combination with old techniques and improve their existing systems. So this talk, for the younger people in this audience, you may not have seen the movie Indiana Jones and the Last Crusade, but in this scene, our hero has found the resting place of the Holy Grail, filled with mystical powers and religious significance, but it's mixed with a lot of other cups and a lot of other options. And the knight who's guarding it explains, the true Grail will bring you life, but the false Grail will take it away. Well, recently I've been working with a couple of clients and I've realized that this is a great metaphor for the current state of caching technologies and the methods we use today. Choose the right implementation, use it well, and your cloud application will scale beautifully. But if you choose the wrong implementation or you don't implement it well, disaster. So let's tell a little story. Recently, I had a client who'd written an application in Java. I'm not going to shame any framework because this can happen regardless of whatever framework you're using. It just really matters about how you use your framework. The application was using InfiniSpan for session caching, so web sessions, user information, things like that. And they thought by using InfiniSpan with a large amount of memory and a number of various nodes to replicate and distribute the cache, that they were going to see significant performance improvements. But they were shocked to find that as they added more instances of the application and scaled the cache accordingly, their performance was actually degrading. They tried to instrument their code and run it through debuggers and not much success. The only thing they saw was that they were seeing about 8 round trips to the cache for every web request, regardless of the size of the request. That's 8 gets and 8 puts for each request to the cache. And each of those gets and push were taking tens of milliseconds. Do the math, 8 round trips, tens of milliseconds per round trip, and you're looking at least 160 milliseconds added on just by pulling things in and out of the cache. Sometimes it was as high as like 300 or 400 milliseconds. Their homegrown instrumentation and timers and logs all just showed the same problem, but there wasn't really a clear cause. And that's when I got called in. Big client, important business application, and they're blaming Red Hat's cache solution, InfiniSpan, Data Grid, as the problem. Well, what's the first question I asked them? You might think to yourself, what's your network look like? How much memory do you have? Things like that. That's not the first thing I asked. The first thing I asked was, do you have tracing and telemetry? What's your observability story? I like to think I'm a pretty smart person, and I've tried to diagnose these sorts of performance problems in the past using homegrown instrumentation and logs and spreadsheets. And you know what happens when you do that? You get a really muddled set of data. For example, I'll show you this in a bit, but adding logging statements can add noticeable latency. Adding cut points and aspects to try and time things can be even worse. It's much better if you use the tools that you're provided in this modern technology infrastructure and ecosystem and many of which are open source, and they can help you understand where your bottlenecks exist. Did I end up with a happy client? I wish the story were better. Unfortunately, there was an architectural problem I couldn't overcome in the short term. The client was storing everything, and I do mean everything, in the session cache. For each user session, the session cache sometimes held as much as 100 megabytes of data. Their cache implementation, which spoke to Infinispan, needed to serialize and deserialize that 100 megabytes of data on every read-write cycle. And additionally, they'd ended up somehow with 2 different servlet filters in their servlet implementation, and both of those servlet filters access the cache. So that's how they ended up with 8 read-write cycles, back and forth, adding lots of latency because of these big complex object graphs that they were trying to binary serialize back and forth. And the advice that I gave them was, A, you need to trim down what you're storing in your session cache and instead do lookups with database caches and control what you store in your cache in a much more granular, nuanced way. Unfortunately, that was going to be a massive effort. That's a pretty considerable rewrite for a typical enterprise application. So it's an ongoing story. We'll see where they end up. But you might ask, how do we avoid this sort of situation? How do I prevent my applications from going in this direction? Or if they're already in this situation, how do I fix them? How do I resolve these sorts of things? There's a lot of cache solutions out there. And what's showing on the screen is just the tip of the iceberg. I'll admit that these are more traditional options. There are newer options which might fit your niche better, and we'll talk about those. And there's been a number of talks today about Eclipse Store, which looks like a new and interesting player in this area. But the question is, which one do you choose? Well, I work for Red Hat. I might be a little biased, but being aware of my bias, I'll try to give you good advice about which ones are going to help you regardless of the choices that you make. I tend to like Infinispan, but you've got to use it properly. Not all caches are equal. Some caches are key value stores. Some caches have schemas and types. Some are distributed. Some are replicated. Some allow you to do database caching. Some are reactive, queryable, persistence, things like that. And each of these capabilities that you might choose in a cache should be considered based on your application's needs. It's not like you can just throw any old cache at any old application in a typical standard way and immediately see performance improvements. It can happen, but more than likely, you really need to think more nuanced. It's not just the cache, right? You could have any of these cache implementations, and if you don't use them correctly or implement them well or choose the correct client libraries or whatnot, you could still end up with problems with the underlying data. Session caches can either contain too little or too much, and you end up with negligible benefit or performance impact even. Database caches work really well as long as the database data is frequently reusable. JCache and native clients allow you for very, very granular control of what goes into the cache, what comes out of the cache, when and how, but they also require more development effort to use them effectively. So in short, there is no simple solution. The first step, though, to using a cache effectively is to use observability, monitoring, tracing. Application performance monitoring is a great first step. Most, if not all, frameworks you might use today support some form of APM or monitoring. You can use capabilities that are built into the JVM, like Java Management Extensions, JMX. Prometheus has exporters for the JVM. You can use proprietary agents like Dynatrace or AppDynamics or Datadog or New Relic, whatever. And you can get some really helpful information about how well your applications are running. For this talk, I'm going to stick to using Prometheus because it's A, open source, B, it's free, and it's well supported by most frameworks. And then we talk about tracing. Tracing, the monitoring, application performance monitoring, gives us the high level of, oh, are we using too much memory? Oh, are we using too much CPU? Oh, are our average request times too long? Are we using too many database connections? But if we really want to see granularly where our bottlenecks exist, that's where tracing becomes necessary. And there are, again, a number of solutions for tracing out there. A lot of the APM solutions have it. There are other solutions as well. For this talk, I'm going to be using open tracing with Jaeger. If I were writing a brand new application from scratch instead of helping a client with a legacy application, I probably would have chosen OpenTelemetry, as that is more modern, more current, more up to date, has a lot more features. But again, I'm using open tracing with Jaeger because open source, supported by most frameworks, and it is free. You can choose to use whichever solution you like. So in terms of the client I was helping, I wanted to build a sort of representative application that I could then use APM and tracing and observability to try and diagnose some issues and help them troubleshoot what they have. Unfortunately, I didn't have the ability to run their application with my hands on their code. We're still working on getting their observability up and running. So I created a typical shopping cart application for our demonstration today and for my client. There's an inventory containing all the products in the database. There's a shopping cart, which is specific to each individual user's session. It holds information about the items in the inventory from the inventory that they have in their carts. There are a number of different places and ways we could use caching in an example like this, but let's start with the naive path. A lot of people, when they're looking to improve performance of especially web applications, web APIs, are going to start looking at like a request or a session cache or a response or a session cache for that shopping cart data. This is persisted, in my case, in a distributed cache. It's read and updated on every request. Now, some of you, I might hear you say, but reads don't update the cache, so not all requests have updates to the cache, right? Well, this is one place where I find a lot of people who are using caches don't realize that every read that you make to a cache has to update the last modified time, because otherwise you could never expire anything from the cache. And caches aren't meant to hold everything forever. So even if you're just reading from the cache, there is a write. And depending on how your cache implementation, cache client library works, it may have to restore the entire object graph for that cache. So the naive implementation, in most cases, could potentially cause you performance bottlenecks if you're storing a lot of data there. For a cache to be effective, like I said, it needs to be able to evict or expire data, and you must update that last access time. And I want you to keep in mind this concept of serialization. Some caches store data as documents. It might be in JSON format. It might be in binary format. A lot of them use something akin to a hash map, a key value. And the value is the object graph or the data. So for example, in the naive path with Infinispan, you've got a key, which is your session ID, and you've got the data, which is Java native serialized binary. So it's taking your Java object graph, serializing it to a byte array, and storing it into the cache. Now, that may not be the right way for you to do things. It could be horribly inefficient for large, complex object graphs. So let's take a look real quick at a basic example of a controller I have for this concept. Can I move this? Yes, I can move that bar out of the way. Excellent. So I have this shopping cart controller. It's a typical micro-profile REST API using JAX-RS. this could run on Quarkus or any of the newer CDI-based frameworks for microservices, and it would look pretty similar. Now, you could do something akin to this in Spring using MVC and Spring Boot. It's not that much different, just slightly different annotations. And we're looking here, we've got, a typical get where we can return the entire shopping cart. We can add items to the shopping cart either via a get operation or a post operation. And what this does is it reads the cart from the cache, adds items to the cart, sets the quantity, and then it writes it back to the cache. Pretty simple. And if we look at read cart from cache, this is a very simple, we'll talk about this in a minute, but the idea is we take our HTTP request, we grab the session, we grab the cart attribute, and that's what we return. Very simple servlet session cache. This is one of the few places in my code where I added some extra implementation to allow me to trace a little more granularly. And we'll talk about why I did that in a little bit. So this is a pretty consistent, pretty simple REST API that you might see. And what I did is I created a load testing application for this. I have a system that I spun up 100 different clients on, each client with a separate session ID, separate cookies, separate session information, running in parallel, doing various different create, retrieve, update, delete operations on the session cache, on the shopping cart, retrieving items from my inventory, information about items from the inventory, and it just ran for hours and hours and hours. And the first step along the way was just this naive implementation of using the session cache. And that naive implementation looks something like this at the application performance monitoring level. So we've got information about our cache hit ratio. This is good. You want your cache hit ratio to be near unity, near 1. If it's much lower than 1, then you might have a problem with your cache. But you can see my scale is 1.00000 to 1. So all of my instances of the application are getting good cache hits. And then we've got our read-write ratio. If your cache is to be effective, you want far more reads than you have writes. That's always going to give you the best performance. So above 1, and the higher above 1, the better in most cases. Average read time from the cache. In fact, this Prometheus exporter that I'm using measures all the way down to nanoseconds, and I could not measure anything. I got zeros across the board. So my read times are fantastic. My cache write times, as you can see, they went up and down a little bit, but never higher than 13 milliseconds. So let's talk a little bit about what's in my cache. When each of these client threads start up, they load a random 400 items from the inventory and store them in the shopping cart cache. So that's 400. There's approximately 3 layers to the object graph that makes up a cart item in this application. And so there's 400 of those items with various details about the item. So every time we update or write that 400 item shopping cart plus the user data, at most it takes 13 milliseconds. Or on average, it takes 13 milliseconds. And you can see over time, as it reached steady state, it got down to around 11 milliseconds. Generally pretty acceptable. Could have been better, especially if I weren't storing the entire cart object items in the session cache. Of course, importantly, we've got our garbage collection statistics. I'm using OpenJDK 11 with the Shenandoah GC. And as you can see, if we focus in, we never had a GC pause more than 170 milliseconds, looks like 173, which is great. 176 is the peak. which means that GCs really weren't causing us any serious issues, and none of the pause peaks across our cluster lined up, which is great, which means that we can handle a lot of users. Next, we've got metrics around our cache expirations and evictions. So if an item is idle for too long or unused or gets deleted, it's going to get evicted from the cache. And you can see that I don't have major peaks in evictions, which is good. If we were having major peaks in evictions, that means we're trying to store too much or more than our memory can handle. And then here's the number of cache entries per node. So you can see it sits around 250, 220 session cache objects per node. We can see how quickly we're getting database connections from our connection pool. This is unrelated to cache, but can have a significant impact. So it's always good to look at this relative to other performance problems. Got our heap and off heap memory. We've got how quickly our responses happen. And you can see we're averaging right around 102 milliseconds for most requests, 100 some odd milliseconds. Very reasonable, not a problem. Down here, we're seeing, I've got an HA proxy load balancer in front, fronting my 3 instances. So each instance is getting around 500 requests per second. HA proxy is handling all of those requests through there. And we can see that response times for HA proxy are actually really, really good. Our average response times are very, very low. Excellent. Now, this tells us very high level. It looks like our application is performing pretty well. We're happy with that. We might see some bottlenecks or something, but it doesn't tell us the whole story, and it doesn't allow us to dig deeper to find real problems. Because even if your application looks like this, which looks pretty good, you might have individual users that have problems, and that's where tracing becomes a major boon. And as I mentioned, we're using Jaeger, we're exporting Jaeger traces. I have this set up to sample 1% of my traces for the application. And at 1%, since I'm doing about 500 requests per second, I'm capturing 5 to 7 requests per second as traces. And if we look here at the time period when I was running this version of the application, you can see, we've got some outliers. 20 milliseconds. That's not great, but it's not terrible. But it's only loading 200 results. So let's set our threshold as 20 milliseconds. And let's see if we have any outliers beyond that. Oh, yeah. Okay. So now we're returning less than 200 results, and we can see our bigger outliers. And I have this request says it took approximately 73.2 milliseconds. And we were mentioning earlier about session caches and how big they are and how quickly and slowly they can be loaded. This is the overall REST request, took 73 milliseconds. If you look at the breakdown, I mentioned earlier that I have this instrumentation code here to check how long it takes for a cache write or a cache read to take using these spans. And if we look here, what we're seeing is the REST request comes in. It takes about, 3 microseconds before it calls to read the cache. The read of the cache takes 41 microseconds. That's trivial. It's nothing, basically, right? What takes longer is this DAO call. This is database operations, right? They take a lot longer. But you see, it's still only like 3.25 milliseconds. So what's happening between here and the time when we write the cache, which again takes 50 microseconds, and then send our response? Why is there such a long pause here? Let's take a look at that code again. So the endpoint that we were looking at is the add item to cart with get. And if we go up and look at add item to cart with get, it gets the parameters and it just calls add item to cart with those parameters. This is what took 41 microseconds at the beginning of the request. The initial delay before we actually read the cache was this, a log statement. Believe it or not, this took longer to do the log statement than it took to read my cache. So interesting. And if we follow down here to read cart from cache, this whole method from the time when we call span start to span finish, 41 microseconds in that call. And then we return the cart. We jump back up here. We're setting a quantity on the item object in the cart. And we're adding the new item to the cart. And then we write the cart to the cache. So between here, somewhere between here and the write the cart to cache is where we're seeing the majority of the time spent. So if we look at this method, we'll see more log statements. So we're actually seeing a lot more slowdowns due to log statements than we are due to cache. That's interesting. That's also valuable to know. So maybe we want to change these log statements to debug level and only turn them on when we absolutely have to. So it appears, looking at our traces, we don't really have a cache performance problem. We have a log slowdown problem. But we wouldn't have known that simply looking at the application performance monitoring metrics. We needed the granularity of tracing to figure that out. So after this initial run, I made some changes to the application. So instead of just doing the session cache, I also went through in the inventory controller. And I added rest easy cache annotations. So this will cache responses for REST calls to the inventory service, the inventory controller. And by making these changes, I expected that certain specific items from the inventory, if you made a request for a specific SKU item by its ID, that you could get a cached response. Now, how often does that happen? Apparently not that often. If we go back and we look at, here are the application performance metrics from that run with the change to use response caches. And you'll see that it doesn't look significantly different other than the number of cache entries increases quite a bit. So we're caching responses. We did see a peak on the database connection pool time, but the rest of them are normal. Response request times all look about the same as what we were expecting. We did have one GC pause that took 6 seconds. So and it aligns with our connection pool time, and it aligns with our response times. So that makes sense. We see that it took longer when we had a GC pause that hit. If we were worried about that, we might diagnose that further, but one GC pause over an hour, not terrible. But what I didn't expect is that when I looked at my traces, I now have a number of events that are taking even longer. So if you look over here, in our naive implementation, our longest running request was 73 milliseconds. Adding response caches, our longest running request was 195 milliseconds. So here's an instance, an example of, hey, I added cache to my application. It should make it run faster, but it actually made it run slower. More than double the response time on our outliers that take a long time. So that's really interesting to see. And if we drill down into this, we actually see that, again, it's not really the cache that's taking so long. This one's actually a database query. This is retrieving a list of inventory items based on a list of primary key IDs. So probably need some better indexes on my database table to handle this, and it would probably run much faster. But still, this request, I just know from my code, this is requesting 400 SKU items from the inventory database. So, I mean, it's bad, but it's not horrendous. 159 milliseconds for quite a bit of data. But again, we see, you know, our read and write cache is microseconds, almost negligible. Our biggest issue here is the database. So then I went in and I was like, okay, if my biggest slowdown is my database, let's implement second level caching in Hibernate in JPA so that we can cache entities and queries in our caching subsystem and get better performance from our database, right? That would be my logical conclusion. So we went into our persistence. Where is my persistence.xml? So I went into my persistence XML and I added these lines. So we're using minimal puts, we're using second level cache, we're collecting statistics, we're using the InfiniSpan cache manager, and Hibernate should cache entities and queries. So when we look at this, inventory DAO implementation, the query that we were looking at is get items ID by list. So we're saying from item I, where I dot SKU is in this list of SKUs. We set the list of SKUs as a parameter and we return the result list. Pretty simple, pretty straightforward. And then we look and see what happens. Well, first off, our number of web cache entries drops off precipitously. Wait a minute, is that the right time? That can't be the right time. And of course, I've got the wrong data. This is, oh, the time was off by several hours. So this should be, day at 3 a.m. GMT to today at 4 a.m. GMT. There we go. That's the right data. Fix my things here. So we really don't see significant differences. Our response times are still in the 20 to 30 millisecond range. Our undertow request times are still in the 100 to 300 millisecond range. We've still got approximately the same number of cache entries. Our write time has actually decreased a little bit, which is great. Cache hit ratio still approaching 1. GC, no significant GC. Well, actually, looks like we had one peak on GC pause around a little over 200 milliseconds. We didn't have any significant evictions or expirations. This all looks pretty good. Again, we go into the traces and we can see that the majority of the traces we have are down around, you know, just a few milliseconds. So let's look for outliers because we're only returning 200 results. Our outliers are going to be above 20 milliseconds. There we go. Oh no, We actually made it worse by adding database cache. So our database cache items, if we look, our longest response time is now 673 milliseconds compared to 195 milliseconds. We added a new layer of cache and our performance on the outliers got worse. That is unexpected, if you ask me, right? I would think you would find that unexpected as well. And so again, if we drill down into this, our database query is still taking too long. Why is this query taking so long even after we added caching for the database? Well, the issue comes down to what is that query doing? And can I even cache that query? So the query that one, get items by ID list, because it's passing a list of primary keys, and by default, Hibernate entity caching stores individual items. Returning this entire list apparently doesn't cache every item in the list. Additionally, up here, when I load the initial shopping cart, those 400 items, something else you'll note is that, where is it? That I'm doing an order by random. Any database administrator will tell you that's a horrible idea because it causes a complete table row scan on every query, and there's no way to optimize it. So intentionally, this is a query that was designed to be non-performant because I wanted to show you in comparison that maybe cache will help your application. Maybe you should look at other things that could be the root cause of your performance problems. And only by eliminating those other bottlenecks can you really start effectively figuring out your cache. So I mentioned earlier that there are other approaches these days. We've heard a couple of speakers today talk about things like Eclipse Store. You can use embedded InfiniSpan. There are other approaches that are more modern. You can use some of the newer NoSQL or NewSQL solutions. Wow, that's tiny. Sorry, I should have bumped up that font size. So NewSQL, NoSQL, oftentimes the NewSQL, NoSQL solutions have caching capabilities built right in. Plus, they're able to optimize based on the usage patterns, depending on how you configure those databases. You can also use distributed or replicated database. I've had some really good luck using things like CockroachDB or Cassandra. Those actually provide you some really decent controls for what gets stored in memory and how, so that you can return your database queries as quickly as possible. And that's still a cache, but a cache at a different level. So in summary, if there's one thing I want you to take away from today is make effective use of observability tools. You can get them for free. They're a little bit of a hassle to set up, but not terrible. And there's also great tutorials out there. If you want to learn about setting them up, reach out to me after via social media or via LinkedIn, and I'd be more than happy to point you at some quick starts that I have that you can use. You need to consider carefully what you're caching and why. The more your cached data is reusable across multiple users, multiple sessions, multiple streams, the more effective your cache can be. So for example, that client I was talking about earlier, they were caching almost everything in the session cache. And because of that, they were duplicating a lot of data in each of those session caches that were technically common across all of the user sessions. So they were storing things like documents that every user had to use, and they were storing things like company common details that every session had to use. But instead, they were sticking in session cache, which means You couldn't share it across every user. Caching is not always a quick fix. You can see from my example, just throwing cache at a problem can actually make it worse if you're not careful and not thinking through how you use those caches. Caching too much can actually be worse than not caching anything at all in some cases. If you're doing what my client was doing and storing 100 megabytes in every user session, that's actually going to impact your performance negatively compared to not caching at all. So with that, I am actually just about right on time and have a few minutes for questions. Feel free to reach out. You can find me on Mastodon as infosec812@fuj.social or LinkedIn. I've pretty much given up every other social media solution because reasons. Won't get into political discussions around that, but if anybody has questions, I would love to hear them.